right, there we go. All right. So we're going to go ahead and get started. I have tests almost completely graded at this point. There's a few left I have to grade. I'm going to grade those basically right after class, and then I'm going to open it up so you can view my comments that I've made on your test. I have circled the problems. When something went wrong, I circled where it went wrong. Or when points are marked down, I circled why points were marked down. And then I will post instructions on how to resubmit any problems that you want to resubmit to get half credit back if you do it correctly. So I will submit instructions on that once I've finished grading everybody's and unlocked the test for everybody to view. So that'll be happening very soon. Overall, I'm pretty pleased. I've seen a lot of really good work. I'm really impressed. So great job. So a little bit later today, look out for that. And I just updated the homework for this week. So I updated homework 5. Okay. All right, any questions before we get started? Okay. All right. So once again, we are working on chain rule. Hopefully you got a chance to practice this a little bit over the weekend. But let's work on doing some more. So basically with chain rule, it's really just, you got to practice it. Practice, practice, practice. So what we're going to do is we're going to practice. So we'll start with sine of square root t plus square root of sine t. Whenever we have radicals, almost always the right step is to rewrite this in its exponential form. So instead of writing square root of t, I'm going to write sine of t to the 1/2 plus sine of t all raised to the 1/2 power. So the root square root t, square root of sine t is the same thing as sine t being raised to the 1/2 power. Now, each of these are going to require chain rule, and they're each going to kind of require chain rule differently. Remembering with chain rule, it's the derivative of the outside multiplied by the derivative of the inside. What was the color coding I was using? Outside was green, inside was blue. So for this guy here, the outside, and maybe I should put that a little lower, the outside is the sine of t, the square root of t. The inside is the square root of t. So the derivative of the outside, so if I look at the outside function is sine of stuff. I can really look at it as just like sine of I don't really care. So the derivative of that, of sine of whatever, derivative of sine is cosine. And you leave the inside part alone. All right, so whatever is in here stays in here. You don't take its derivative. So this would be cosine of t to the 1/2. This is the derivative of the outside. Then the derivative of the inside is the derivative of t raised to the 1/2 power, and we're going to use power rule on that. So the exponent comes down, and then subtracting 1 from 1/2, you get negative 1/2. Plus, now for this guy, the outside function is this guy. So I don't care what's on the inside when I'm doing the outside function. I just know that it's being raised to the 1/2 power. So when I take the derivative, it's 1/2, and then the stuff on the inside stays the same, raised to the negative 1/2, because I'm using power rule on the outside. In this case, the inside stuff is sine t. So sine t would stay on the inside. So I have 1/2, sine t stays on the inside, raised to the negative 1/2. And I probably should have wrote right here that this is the derivative of the inside. And then the inside part is sine t. So the inside is sine t, and the derivative of sine t is cosine t. And that would be your final answer there. So f prime of t is equal to, and I mean, if you wanted to, you could simplify it a little bit. You could move things around, but you don't have to. I'm just going to write it as cosine of t to the 1/2 power times 1/2 t to the negative 1/2 plus 1/2 sine t raised to the negative 1/2 times cosine t. So for that one, those were just, we had two chain rules that had to be done side by side. Now, for this next one, this is actually like a nestled chain rule. So we have chain rule within chain rule that needs to happen here because there's not just one inside. So we have this very inside function, which is w squared plus 1. We have this inside but not fully inside function, cosine of w squared plus 1. And then we have this outside function, sine of cosine of w squared plus 1. So we need to kind of do this in steps. The first step we're going to do is, the first thing we have is sine of stuff. All right, we have sine of stuff. And if we take the derivative of sine of stuff, then it's the derivative of the outside. So the derivative of sine is cosine, and the stuff remains the same in the inside. And then times the derivative of the stuff. So starting our derivative here, we're starting with this idea, sine of stuff. Derivative, cosine of stuff. So cosine of everything on the inside here. So cosine of, leave everything in here alone, right? Leave everything in here alone. So cosine of w squared plus 1. Let's see, wait, hold on. Too many parentheses there. So that's the derivative of the outside stuff. Now I'm going to say we're multiplying it, and I'm just going to write the notation. So the derivative of cosine of w squared plus 1, right? This right here means the derivative of cosine of w squared plus 1. For this guy, this is the outside function, and then the inside function is the w squared plus 1. So the outside function, his derivative would be negative sine w squared plus 1, because if you have cosine of whatever, the derivative of that is going to end up being It's okay. My pen's just angry because it has little battery, but then my other one's charging, so it'll be fine. Negative sign, the stuff in the inside remains the same, and then you multiply by the derivative of that stuff on the inside. So multiplied by the derivative of w squared plus 1, which is 2w. So you're putting this all together. So this whole thing had this derivative. So cosine of w squared plus 1 had this derivative. And then you're multiplying it with this beginning part. So altogether, we have cosine of w squared plus 1 multiplied by negative sine of w squared plus 1 multiplied by 2w. And I am going to give you guys some to practice on. I'm going to do this last example on here, and then I'm going to give you guys some to practice. But can I answer any questions about those first two while I'm waiting, before I do this next one, that is? I'm grabbing some examples online to use for. Yes. Yes, absolutely. So if you didn't have parentheses on this guy, that would be a problem. So if you had cosine, I'm glad you asked that, of w squared plus 1, negative sine, if you wrote it like this would mean minus sine as opposed to multiply by negative sine. So there's times when parentheses aren't necessary, and then there's times when they are. To err on the side of caution, I would say just put them always, because it's easy to run into those situations where they are necessary and you're not putting them. And it never hurts to have extra. So for instance, you don't necessarily need parentheses. Let's see, where's a place where you don't need them? Technically, these parentheses right here are unnecessary. However, that's basically the only set of parentheses in this entire thing that's not necessary. Does that help a little bit? No problem. Any other questions? Okay. Sorry, still scrolling to see what problems they have in this chapter that I can give you to practice on. Okay, we'll do this one, and then I might just make up some of my own. All right, first of all, because it might be a little bit blurry on the screen, I'm going to rewrite this. So you can read it a little better. So the original function is k of x is equal to e raised to the x cubed minus 7x squared plus 2. We have an outside function, and then the inside function in this case, when you have e raised to the whatever, the inside function is going to be that exponent. So really we have e raised to something, doesn't matter, and the derivative of e is just e, right? So his exponent will stay the same when we do the outside derivative. So k prime of x is equal to, we're basically leaving the whole thing alone because the derivative of e is just e. But now, because there's stuff in the exponent that's not just x, we take the derivative of the exponent and we multiply it down here. So the derivative of the exponent would be, just using power rule, 3x squared minus 14x. So in general, a rule that you can use if you have e raised to whatever an exponent, typically the way we do it, typically we end up writing this part out front because it's a little bit easier. So it's the derivative of the exponent times just e to the whatever, the original function. So for instance, if I'm taking the derivative of e to the sine x, I would take the derivative of the exponent, which would be cosine x, and then multiply it by the original function, which was e raised to the sine x. If I had the derivative of e raised to the 5x cubed, the derivative of the exponent would be 15x squared, e raised to the 5x cubed. So this thing just stays exactly the same. All right. I'm going to give you guys a few to try and see how this one goes. So let's do f of x equals ln x plus x squared cubed. Let's do this guy. And this, and one more. This guy. All right, so I'm going to stop the recording for a second and then put on a timer, I think, for let's say 5 minutes and work through these problems. And then we'll come and talk about the answers to these. So get the first derivative to all of these. Once again, this right here is a 3. It's cubed just because it kind of looks a little tiny there. All right, pausing the recording. All right, so my timer just went off. So let's go ahead and work through these. For this first one, the outside function is this big guy. So we're bringing down the 3. We're using power rule, leaving the inside alone. And then we lower the power by 1. So that's the derivative of the outside. The inside is this part here. So I'm going to use parentheses. The derivative of ln x is 1 over x. And then the derivative of x squared is 2x. And that would be the full derivative there. Questions on that one? Okay. For the next one, the outside function is tangent. And remember that the derivative of tangent, just regular tangent, is secant squared. So the derivative of the outside is going to be secant squared, and we'll leave the inside alone. And then the derivative of 5x is just 5. For this next one, I'm going to rewrite this. So cosine cubed is the same thing as cosine, and then rewrite the inside part, all being cubed. So it's like that cube is on the outside. So this one's going to have 3 layers of it, where the most outside layer is this guy. The second layer is this guy, and then the third layer is this guy. So there's 3 layers. So starting with that most outer layer, you have, let me just write parentheses that don't look like squares. If you have something that looks like this, you're just using power rule. For the next layer we have, if you have cosine of something, right? Not thinking about the chain rule at this moment, just cosine of, let's just say x, that derivative ends up being negative sine. And then for the inside, most inside part, that's all just power rule. So the derivative of the most outside, 3, and then we leave the inside part alone. Bring down the power. Then going to the next layer, which is the cosine layer, the derivative of cosine is negative sine. Leave the inside alone. And then the derivative of the most inner layer is the t squared plus 3t plus 1. So that's 2t plus 3. And that whole thing there is the derivative. For this last one, this is going to be a product rule problem because we have 2 different pieces here. That are being multiplied together. Remember, for product rule, it's f prime g plus g prime f. So this guy's f, this guy's g. So f is x squared, which means f prime is 2x. G is sine of 5x. The outside function is sine of 5x. The inside function is 5x. So the derivative of sine 5x is going to be, derivative of sine is cosine. Leave the inside alone, so leave 5x alone. Cosine times the derivative of 5x is 5. So our full derivative here, j prime of x, so that's f prime g, so 2x times sine of 5x, plus g prime, so g prime is cosine 5x times 5, g prime times f, which is x squared. If you wanted to rewrite it a tiny bit, just to kind of bring the x's out front. It would be 5x squared cosine of 5x. But either of these answers work. How did that go for everybody? Good, good. Any questions or anything about that? Excellent. Okay. And as a reminder, if you have questions and you don't feel like even typing them to everybody, you can always send it as a private message to me. So don't feel afraid to ask questions. If you're confused, please ask questions. Ask, even if you don't have a question to ask, say like, oh, wait, could you explain that again? Any of those things. You can say things. Please don't feel afraid to say things. All right. So we have, in this next example, we have t of y is equal to pi raised to the cotangent of y. And as a reminder, so first of all, pi is just a number. So the derivative that you use is the derivative of a raised to the x. And the derivative of a raised to the x is ln of a times a to the x. So in the case of pi, the derivative, which is just a number, the derivative of pi to the x would be ln of pi times pi to the x. Now we don't just have pi, right? We have pi cotan raised to the cotan y. So in that case, the derivative we're looking at is going to involve ln of pi times, we're really just replacing, for the outside derivative, we're just replacing the x with a blank. So times pi to the whatever times the derivative of whatever's in that exponent. So in action, t prime of y, the derivative of the outside, ln pi times pi to the cotan y, so that stays the same. And then the derivative of the inside, which is cotan y. And the derivative of cotan y is negative cosecant squared. So maybe I'll make a note over here. The derivative of cotangent x, just because it's been maybe a few minutes since we've seen it, is negative cosecant squared x. Right. Let's talk about ln's, because ln's are kind of special in a way. There's a lot of special things. First of all, ln's have a lot of rules that allow us to do fun things that we're going to do on, I think, the next page. There's some fun special stuff about ln. So I'm going to do this derivative regular, and then I'm going to talk about how we could write it nicer. So here we have ln of, there's stuff happening in there, right? So we have like an outside function, which is the ln part, and we have the inside function. As a reminder, the derivative of ln x is 1 over x. So in this case, we're replacing, the inside with the x with the inside part. So starting this derivative off, the derivative of the outside, we have 1 over the inside part, which is 7x to the 5th minus 4e to the x cosine x. That is the derivative of the outside. It is derivative of ln x. Oops, let me point. Derivative of ln x. So 1 over x, 1 over the inside. Now we're multiplying it by the derivative of the inside. So this first part, derivative of 7x to the 5th, that's just 35x to the 4th, minus this part requires chain rule. This is f, this is g. Not chain rule. Product rule. Not chain rule. Product rule is what I meant to say there. Product rule. So f is going to be 4e to the x. F prime is 4e to the x. G is cosine x. G prime is negative sine x. So product rule f prime g plus g prime f. So f prime is 4e to the x. G is cosine x. Plus g prime is negative sine x. So instead of doing a plus, I'm just going to leave it as a minus because it'd be plus a negative. So negative sine x is g prime. And then times f is 4e to the x. And that would be my entire derivative, which is cool. And the answer, we can box this. That's really neat. But I kind of want to think a little bit deeper here because there's actually an easier way of writing this. Not significantly easier, but easier enough that it's worth mentioning. If you're taking the derivative of ln of stuff, this ends up being 1 over the stuff times the derivative of the stuff, right? That's what ended up here, right? Here's 1 over the inside part, and then the derivative of the inside part. Right, I could write the word inside down here. But just basic fraction multiplication, 1 over blah, 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 blah. I don't care. Let's just use 2 times 7. If you're doing 1/2 times 7, really it's 7 over 1. You do 1 times 7 over 2 times 1. That's how you combine it, right? And you get 7 over 2. My point being, if you're multiplying 1 over something by something, it's really just multiplying that something in the numerator. It's really just putting that something into the numerator. So this is the same thing as the derivative of the inside over the inside. And it's a faster way of writing it, so it doesn't have to be all spread out. So this whole thing could have been written with this part in the numerator. And it's kind of easy to think of derivatives of ln as being the derivative of the inside over the inside. It makes it really quick. So, for example, if you're doing the derivative of ln of, let's say, no, let's not do e to the x. Let's do tangent x. The derivative of tangent x is secant squared x over the inside, just tangent x. right? This is technically chain rule. Normally we would have written it as 1 over tangent x and then multiplied by secant x, secant squared x. But it's the same thing, right? Secant squared x over tangent x is the same thing as 1 over tangent x times secant squared x. So something to kind of think about. It's a little bit easier. All right, try this one out. This is going to be another 3-layered one. I want you to try this one out. The e to the cosine x cubed. I'll put a minute and a half on the timer, give you a minute and a half to do the chain rule for this one. So e raised to the cosine of x cubed. It's going to be one of those 3-layered ones. There we go. That was the timer. So 3 layers here. First layer being the, let me underline it, e part. Next layer is the cosine part. And then the final layer is that x cubed part. Okay. So with the e part, we just simply leave it alone. Leave everything alone. Just leave it the way it was. Then derivative of cosine is negative sine, and we leave the inside alone. And then finally, the derivative of x cubed is 3x squared. And that would be our final derivative. Any questions, comments, concerns on that one? Hopefully it's kind of coming along. It takes a little bit of time, but hopefully it's coming along. Okay. So let's talk about fun things we can do with logarithms. Let's remember some log rules real quick. Quick log rules. If you have log or ln and log are the same thing. If you have log of, they're not the same thing, they're different bases, but they have the same rules is what I mean, of a times b, then this can be split up into addition on the outside. So multiplication on the inside turns into addition on the outside. So log a plus log b. If you have log of a raised to the c, that exponent can come down in front. And you can just leave it as c times log a. And if you have division on the inside of log turns into subtraction on the outside of log. Right, maybe I'll do a quick example of this. So if you have log of, let's just say 5x, you could separate this because 5 and x are being multiplied into log 5 plus log x. If you have log of x squared, you can bring that exponent down in front, and this would be 2 log x. If you have log of, I don't know, let's say 7 over x, you could separate this into log 7 minus log x. This might not seem like it has like a ton of uses. Maybe it does, maybe it appears to you right away. If it doesn't appear to you to have a lot of uses, I'm just going to tell you, spoiler alert, this is so useful because we've already learned how annoying product and quotient rule are, right? Looking at this problem right here, if I'm looking at this, oh my goodness. Okay, so I'm going to have to do, first of all, this would require chain rule, right? So I'm going to have to do chain rule and then quotient rule on the inside of that. Like that's a lot, right? That's quotient rule inside of chain rule. That's going to be a really kind of gross looking. answer. But if I use my log rules here, then I can make it simpler before taking the derivative. So the trick is to expand using log rules first. Before taking the derivative. So this is division, so it's division on the inside, so I can split it into subtraction on the outside. So I have ln of sine t minus ln of t squared plus 1. I have not taken a derivative, and that's really important to take note of right now. I have not taken a derivative. I have used algebra. Log rules belong under, I guess it's pre-calculus, but I'm going to call it algebra. We have just done algebra. We have not done any derivatives yet. As a note, this part right here, t squared plus 1, cannot be expanded anymore. Clap when I say it. Cannot be expanded anymore. It is done being expanded. If there's addition in here, I can't separate addition. I can separate multiplication. I can separate division. I can separate if there's one exponent, but I can't even take this exponent down because it's only on him. It's not on him as well. So once you get down to addition or subtraction, and that's what's left on the inside, you're done separating. But this makes the derivative a lot easier for us to take. Because now, remembering our log rule, so if you're taking the derivative of ln of stuff, it's the derivative of the inside over the inside. So the derivative of sine t is cosine t all over the inside, which was sine t. Right, this is the derivative of the inside over the inside. And we can do that same thing for the next one. The derivative of t squared plus 1 is 2t. The inside is t squared plus 1. And that's my entire derivative. To be clear, if you were taking this the long way, your answer would look much, much different. All right, this would require a quotient rule. So why don't I just kind of write what it would look like, because I think it's interesting to talk about how bad this could look if we wanted it to look bad. You would have an f and a g, right? And our rule would still be the same, where like derivative of the inside over the inside. So the inside itself would be sine t over t squared plus 1, right? That's the inside. So then we put the derivative on top. Quotient rule requires f prime g minus g prime f all over g squared. So f prime, that's going to be cosine t times g, which is t squared plus 1, minus g prime, 2t, times f, which is sine t, all over g squared, so t squared plus 1 squared. And then making sure that this is the big fraction line. That would be your answer if you did it the long way. This whole thing is the same as this, believe it or not. It actually all works itself out if you simplify it all the way, where this is this, but this is way worse to write. And you can do that, right? I'm not going to ever penalize you for doing that. It's just you can make your life so much easier by not doing that. Yes, it is much more simple to do this. In fact, it is so much more simple that we're going to get into situations where there aren't LNs at all, but we introduce LNs just so we can use this property. It makes it a slight bit, there's like an extra step involved, and we'll talk about it in the next section. There ends up being an extra step, but the step is worth it so much that we introduce a new step just so we can take advantage of the rules that logarithms give us. It's really, really important. So let's look at this guy. A few things here. We're going to use algebra to rewrite it, and then we're going to use log rules. But additionally, something to remember that the derivative of log base b of x is 1 over, I forgot how we wrote it. Did we write it as 1 over x times 1 over ln b? I can't remember if we wrote it like that or if we wrote it because there's a million ways of writing it. Let me just make sure I'm consistent. All right, we wrote it as 1 over ln b times 1 over x. I mean, it's the same thing. Oh, come on. So I'm going to start with rewriting with exponents, then expand using log rules. So we have c of q. Q is my least favorite variable, just in case you're wondering. It's between p's and q's. So why don't I just quickly talk about why Q's are just the worst variable in the world, because I feel like everybody needs to hear this. Q's are the worst variable in the world because I taught a lot of business calculus when I was teaching at The Ohio State University, and you use Q's for quantity, and that's used a lot in calculus, as you can guess. But some people don't write their Q's right, so some people write Q like this. So if they're writing 9Q, it's like this. And I'm sorry, but if you don't put a tail or a hook or something on your Q, it's a 9. And it led to a lot of frustration. So that's why Q's are the worst variable in the world, and that's why I dislike Q's as variables. And just the letter Q in general, it just doesn't feel like a great letter. I feel like there's much better letters than Q. Like, I like the letter G. I think G is a nice letter, but I don't think Q is a nice letter. Thank you for attending my TED Talk. Moving forward. So someone in the chat saying that's why I hate t variables, because they look like a plus. I would agree with you. However, so once I got into, I guess, calculus is when this started for me. I write my t's like this when I'm writing, so I don't write them with a little curly. But in math, t's always have a very definite curly on them. So I encourage my students. I love using t's as variables because curlies. Just put a little curly at the end. I don't do it when I'm writing, but I do it when I am putting t as a variable. And then it's very definite that it is different than a plus sign. Yeah, that's when it started for me. Calculus is when it started for me too. Just for this class. And that's okay. You don't have to do it with the rest of your letters. You just do it with your math t's. And then you'll start to love it, slowly but surely. All right. Now I've finished my TED Talk on why Q's are awful variables. So I'm going to rewrite this guy as q cubed minus 4 raised to the 1/2 power. And then I have that log rule that says, hey, you can take this exponent down in front And this is not a derivative. This is not power rule. This is a log rule. I have not taken a derivative yet. This is just a log rule that kind of feels like it's a, what's the word? Like it feels like a derivative, feels like power rule. So now taking the derivative of this guy here. So that 1/2 can go ahead, this 1/2 right here. It's just going to stay in front. For log base 5, the only thing that we're doing different we're going to be doing different, is it more work to do it this way? Maybe, but that's okay, is that we have an inside part here. And instead of it being ln x, where you don't need to have this ln b, you're going to have 1 over ln b times, and then just the ln rules, right? So deriv of inside over inside. Where the inside is this part here. So we're going to have 1 over ln of the base, which is 5. So 1 over ln 5 times the derivative of the inside. So the derivative of q cubed minus 4 is 3q squared over the inside, which is q cubed minus 4. Now, I'm going to tell you that technically I don't need to have parentheses on this denominator part. If I was going to write it as one fraction, I would need to have parentheses there. But because there's multiplication between each of the fractions, it is implied that this thing is all together. However, if I were going to write it all as one, if I was going to do that, it would be 3q squared 2 ln 5, and then I would have to write q cubed minus 4 like that if I wrote it all together as one fraction. But if you put parentheses in here, it's not wrong. It's just unnecessary, but not wrong. Still accepted. It's a big 4. Yeah, so it's because it's from right up here, where the 4 is big. Other questions? All right. So I want you to try, well, maybe I'll do one more with you on this one. Okay, let's do one more of these and then I'll give you some to try for this. So first step is rewriting. We're going to do this in steps. So first of all, I am rewriting the radical as a exponent of 1/2. That's my first step that I'm doing. I'm just rewriting at this point. This 1/2 can come down in front because we have a log rule that says we can do that. So we have 1/2 ln 2e to the 3x plus 1 7x minus 2. And now we have division, and we can separate that with subtraction on the inside. So I'm going to put big parentheses here because the 1/2 technically belongs on all of it. 1/2 ln of 2e to the 3x plus 1 minus ln 7x minus 2. So if you had me for Math 126, and if you remember anything from Math 126, I spent a lot of energy talking about expanding these things. I I spent a lot of energy and time talking about shortcuts of expanding them. So I talked about how to get from here down to a final answer. I talked about that. And then I also, we just spent a lot of time working with logs. And the whole reason that we spent a lot of time working with logs is that when we got to this point here, that you have all the tools necessary to do calculus with logs and not be uncomfortable with them. So now I'm going to take the derivative because I haven't taken the derivative yet. This 1/2 can just stay out front because it's a constant, so I can just ignore it. Now the derivative of the inside over the inside for both of these. For this guy, remember with e to the whatever that the derivative is going to be, you could write just derivative of exponent times e to the whatever its exponent was in the first place. So in the case of e to the 3x, the derivative of the exponent is 3 e to the 3x. That would be the derivative of that guy. Now, if you have 2 e to the 3x, the derivative is 2 times 3 e to the 3x, which would give you 6 e to the 3x. So the derivative of this guy here, the first part, that's 2 times 3, so 6 e to the 3x, and then the derivative of 1 is 0, over the inside, which is 2 e to the 3x plus 1, minus the derivative of 7x minus 2 is 7, and then over 7x minus 2. And there's your entire derivative. I don't even need to explain to you how awful this would be if you tried to take it outright, because you'd be doing, first of all, triple chain rule with a quotient rule. It would be a really gross derivative. It might be worth just you spending time taking it just to see how awful it would be, so that you understand that it's awful. All right. Let me grab a few for you to practice that involve LNs. Oops. Let's do f of x equals ln of square root sine x minus 5x cubed. All right, I'm going to set a 5-minute timer for you to work on this, and then we'll come back and talk about it. So separate them first, then take the derivative. All right. So that timer just went off. So Let's use some log rules to make these better. Rewriting this guy can be rewritten as 1/2 ln sine x minus 5x cubed. So the derivative, we'll just leave the 1/2 out here. The derivative of sine x minus 5x cubed, so the derivative of the inside, is going to be cosine x minus 15x squared. All over the inside is sine x minus 5x cubed. Oops. For this next one, this can be rewritten in a few steps. When it comes down to it, you're going to get ln of cosine 4x plus 1 minus 3 ln 5x minus 9. So this 3, once you've separated everything, then this guy would have a cube in the inside, and you can bring that down. So the derivative for the first guy, so the inside part, right, is cosine of 4x plus 1. And then derivative-wise, we have to do chain rule. There is a little bit of chain rule we have to do here. So the derivative of the outside would be negative sine, leave the inside alone. And then times the inside, the derivative of 4x plus 1 is just 4. Minus, the 3 can just kind of stay out front, that's fine. This 3 right here. And then the derivative of 5x minus 9 is 5. And the inside itself is 5x minus 9. So if you wanted to rewrite this just a little bit to be a little bit nicer, you could put the negative and the 4 together up here. So you could write it as negative 4 sine of 4x plus 1 over cosine of 4x plus 1 minus, and then you could multiply the 3 and the 5 together if you'd like, and then you have 15 over 5x minus 9. Either of these derivatives will work. Right. This last one takes a few steps of separating things, which is something you may want to practice. I think I might still have a video on expanding logs. Let me go double check on that right now. I think I have one, because I think that was that was towards the end of the class, and I don't think we were in class for that in the spring. Properties of logarithms. I have a whole lecture on that. So I will post that lecture so that you can see how to, I talk about tricks on how to get it really fast, how to separate these really quickly. So I will post that video on Canvas for you to look at if you are struggling to see what I'm about to do here, because I'm about to make it a little bit fancy. So this would separate into 1/2 ln x plus ln of tangent x minus ln of x plus 5 minus ln of 2x minus 1. So the whole expansion of that comes out to be this. And then I'm taking the derivative. So for the first one, the 1/2 stays, and then the derivative of ln x is 1 over x. Plus, the derivative of tangent is secant squared. and then the inside is tangent, minus the derivative of x plus 5 is 1, so 1 over x plus 5, minus the derivative of 2x minus 1 is 2, over 2x minus 1. And that is the entire derivative. So once again, if you're having trouble with this part here and how I could do that so quickly, I am going to post that video so that you have that available to you and you can see how to get from here to here in no time at all. I think I go through some pretty complicated examples. I do. So I go through in the video, one of the examples I go through is ln of x squared times x minus 7 times the square root of 2x plus 1 all over x plus 1 to the 6th times x minus 1 squared times 4x plus 9. I talk about expanding this. So, and I do it in one step. So you don't need to write this down. I'm just kind of showing you this is the type of thing I talk about in the video, how to get from here to like completely expand it in one step. And then calculus just takes the extra step of taking its derivative once you get there. So I'm not going to write that down, but I will post the video. Any questions or comments on those before I move to the next step? Okay. All right, so it's really important that you recognize that you can only do log stuff, log rules, if you have logs. I don't have any logs here. I cannot use log rules in a situation where I do not have logs. So because there are no logs here, I cannot use log rules, and that's important. We are looking at a chain rule situation where we have an outside, and then the inside is this part here, that whole quotient rule. So the derivative, we'll start with the outside function, which is just something raised to the 7. So power rule, leave the inside alone, lower the exponent. So I have 7 times x squared plus 1 over x cubed plus 2x minus 3, all raised to the 6th power. And then for the derivative of the inside, we have a quotient rule that we need to do. So for quotient rule, we have x squared plus 1 as our f, and so f prime is 2x. G is x cubed plus 2x minus 3. G prime is 3x squared plus 2. And remember quotient rule. F prime g minus g prime f all over g squared. So f prime g, so 2x times x cubed plus 2x minus 3 minus g prime is 3x squared plus 2 times f is x squared plus 1. And then g squared, so x cubed plus 2x minus 3 quantity squared. And that big whole thing right there is the derivative. All right. For the next one, this is going to end up being product rule and some chain rule involved. So you have two functions being multiplied together. For product rule, that's f prime g plus g prime f. So f, e to the 4x squared. For that derivative, we have to use product rule. And remember, with ease, it's the derivative of the exponent times the original thing. So the derivative of the exponent is going to be, right, 8x. So 4x squared, the derivative of that is 8x. And then e raised to the 4x squared. So leave that part alone. For g, we have tangent of ln x. This is the inside part, outside part. For g prime, the derivative of tangent is secant squared, and then leave the inside alone. So you have secant squared of ln x. And then the derivative of the inside, the derivative of ln x, is 1 over x. So our derivative of y, f prime, so 8x e to the 4x squared, times g, which is tangent of ln x, plus g prime, secant squared ln x, times 1 over x, times f, e to the 4x squared. All good there. So let's move on to a graph example. A graphing example. So we have a graph. This is the graph of g. This is the graph of f. So let me make, this says g of x. This guy right here says f of x. So the dashed lines are f of x. The blue line is g of x. And then there's a third function, h of x, that has information over here. This notation, remember, means evaluated at x equals 1. So the derivative evaluated at x equals 1. Take deriv, then evaluate at x equals 1. To remind you of the full definition of chain rule that we talked about in the very beginning, like maybe I should scroll back so that you can see it. The very first definition I gave of chain rule was this guy right here. F prime, if f of x is equal to f of g of x, then the derivative is f prime of g of x times g prime of x. And I said that this was the derivative of the outside, and that's the derivative of the inside. So I'm going to just copy and paste that. So if you have a composition of functions, that's what that derivative turns into. In the case that we're looking at down here, this is f of h of x. So instead of g, we'd have h. So the derivative of f of h of x, using just this formula we had from before, it's this, but the g's are h's because we're taking the derivative of this. So it's f prime of h of x times h prime of x. If we're evaluating at 1, we would have f prime of h of 1 times h prime of 1. So we're just replacing the x's with 1s. Okay. H of 1 we can get from the table. So h of x, if x is 1, h of x is negative 1. H prime of 1, here's h prime, here's 1, is 3. So now we have f prime of negative 1 times, oops, let me see, this should be equals 3. So f prime of negative 1 times 3. So f is the graph of f, right? We're looking at f, and we want his derivative at negative 1. And negative 1 is right here. So this is the slope of tangent line of f at x equals negative 1. Negative 1, not positive 1, right? We had to plug 1 into h to get a number out, and then we plugged it in, and now we're going through another step. So the slope, because this is a line right here, this is just a line, the slope of the tangent line is just the slope of this line. So to figure out the slope of that line, we can use the slope formula. So this is the point negative 2, comma 1, and this is the point 0, comma negative 1. So f prime of negative 1 is just the slope of that line. So you're doing y2 minus y1 over x2 minus x1. y2, and it doesn't matter how you label these. This could be x2, y2. This could be x1, y1. So y2 is negative 1 minus y1 is 1. x2 is 0 minus x1 is negative 2. So that's negative 2 over positive 2, which is negative 1. So this comes out to be negative 1 times 3, and the answer is negative 3. So it's kind of working through the definitions and then being able to interpret from the graph. For this next one, it says we have a function k, and it's equal to g, and then you sine x on the inside. So this is like this composition here, except for, in this case, instead of f, we have g, and instead of g, we have sine x. So if I'm using this rule up here, k of x equals g of sine x, the derivative, right? Instead of f, it's g on the outside. So the derivative is g prime of sine x because g, the inside part, is now sine x. Maybe I can color code this a little better. I think that would make it a little easier to do. G is the same thing as f in this case. And then sine x is the same thing as g of x. So here, f prime is actually g prime, and g of x let's see. Okay, that just completely died. Hold on a sec. Okay. There we go. So this will be sine x in the middle here times, and then once again, instead of g, we have sine x. So this g prime here of x is actually the derivative of sine x. So the derivative of sine x is cosine x. This is the g prime part from here. So we're going to find k prime of pi. So k prime of x, without plugging anything in, is g prime of sine x times cosine x. K prime of pi would be plugging pi in. So we have g prime of sine of pi times cosine of pi. Sine of pi is going to be 0. Cosine of pi is -1. So we have g prime of 0 times -1. To get g prime of 0, we need to look at the graph. So this is going to be the slope of the tangent line of g at x equals 0. G, remember, is the blue graph here. And the tangent line, if you look at 0, is going to be flat. It's going to be horizontal because it's at the bottom of a hill. And that slope is 0. The slope of a horizontal line is 0. So this would be 0 times -1, which is 0. So we did the first part. We found k prime of pi. K prime of pi is 0. Then it says to find the line tangent to the curve k at x equals pi. So remembering what we need to find the equation of a line, for a line, you need a point, so you need an x1, which in this case they gave us, they told us it was pi. We need a y1, which we need to find still, and then you need a slope, which is m. And that's going to be k prime of pi in this case, because the derivative of the tangent, like the derivative gives us the slope of the tangent line, and we're looking for the tangent line. So we already found this. This was 0. So the only thing left to find is y of 1. And that's going to come from this original equation. That's going to come from plugging in pi, the x value, to the original equation. So g of sine of pi. Sine of pi is going to be 0, so it needs g of 0. So we go to our original equation, our original function. Here's g. G of 0 is the y value at 0, which is 1. So our line here, remember y minus y1 equals m times x minus x1. Y1 is 1, m is 0, x1 is pi. 0 times anything, that's just going to be 0, so we have y minus 1 equals 0, or y equals 1. So there's a lot of steps there. It's quite a few steps, but you're taking that derivative definition of chain rule, and then you're just applying it and remembering all the things that we've already done in terms of finding tangent lines. You need a slope, you need an x and a y value. They gave us an x. For the y value, we just took the original function and we plugged in pi, which was the x value. And then for the slope, that was k prime, so the derivative at pi, which we found here to be 0. Can I answer any questions there? If there is a question, I'm happy to go back. So we'll do one more of these where it's kind of abstract. So we have f and g are differentiable functions. We're given a bunch of information about derivatives and about the original functions. We're told that k of x is g composed with f of x, and to find the equation of the line tangent to k when x equals -3. So k of x is equal to g of f of x. Using our definition of chain rule, this derivative is g prime of f of x times f prime of x. We're looking for the equation of the line tangent to k when x equals -3. So again, for a line, we're going to need an x1, which they gave us, -3. We need a y1. And this we get from plugging in the x value to the original function. And then we need the slope of the tangent line, which comes from plugging in the x value to the derivative. So I'm going to work on slope first. I'm now plugging in my x value, -3, to the derivative. There's two values I can fill in right now. So I have f of -3, and then I have f prime of -3. Coming up here, let's see, f of -3 is 1. F prime of -3 is 2. So I have g prime of 1 times 2. G prime of 1 is 5. So I have 5 times 2. This is 10. So k prime of -3 is 10, which is our slope, m. For finding y, we're plugging x equals -3 into the original function. So here's our original. So k of x equals g of f of x. So k of -3 is g of f of -3. F of -3, once again, we already found that was 1. Now we need g of 1. And g of 1 is -5. We now have x, y, we have m. That is everything we need to do y minus y1 equals m times x minus x1. Y plus 5 is equal to 10 times x plus 3. So y plus 5 is equal to 10x plus 30, subtracting 5 on both sides. Y equals 10x plus 25. So I know the last 2 questions, the graphing one and this one, are more on the conceptual side, but it's important to kind of think of these things in a conceptual way. It's important to think about what chain rule actually means. There are several examples, I think, in the exercises for this section that go over more conceptual type problems. So I definitely suggest practicing those. I think for today, that'll be it. I mean, we have 3 minutes left, but I'm not going to start a new section today. I have posted the homework, like I said. I will also be finishing grading those tests basically right now that I have left to grade, and then I will post all of the test results, and I will post instructions on how to resubmit your exam along with a deadline, which should be next Monday. If you have questions, I will stick around to answer them. Otherwise, you are free to leave and have a fantastic Monday.